Welcome to the Sleep and Learn channel. We invite you to listen to interesting scientific facts that will help you fall asleep gently and, at the same time, learn something new. Relax, close your eyes, and let a calm voice guide you into the world of knowledge and sweet sleep. The quiet architecture of the Earth. Geology is the study of the Earth's structure, materials, processes, and history. It is a science measured not in minutes or years, but in eons. While many natural sciences focus on movement and change at visible speeds, geology reveals transformations so gradual that they often escape human perception. This slowness is one of its most calming qualities. The mountains rise and erode, oceans open and close, and continents drift, all at a pace that encourages reflection rather than urgency. The Earth formed approximately 4.54 billion years ago. Over this immense span of time, layers of rock accumulated like pages in a vast natural archive. These layers, preserved in cliffs and canyon walls, record ancient oceans, deserts, volcanic eruptions, and even the footprints of long-extinct animals. Each stratum is a chapter, composed not of ink, but of minerals and sediments. Rocks are traditionally classified into three main types: igneous, sedimentary, and metamorphic. Igneous rocks originate from molten material beneath or upon the Earth's surface. When magma cools slowly underground, it forms coarse-grained rocks such as granite. When lava cools rapidly at the surface, it produces fine-grained rocks like basalt. The cooling process itself can be imagined as a gradual settling, heat dissipating, crystals arranging themselves in quiet order. Sedimentary rocks form through accumulation. Wind, water, and ice carry tiny particles across landscapes, depositing them in rivers, lakes, and seas. Over time, pressure compacts these sediments into solid layers. The rhythm of sedimentation is gentle and repetitive, like breathing. Grains settle, layer upon layer, creating patterns that resemble soft stripes in stone. Metamorphic rocks begin as either igneous or sedimentary rocks, but are transformed by heat and pressure deep within the Earth. This transformation does not melt the rock entirely. Instead, it reorganizes its internal structure. Minerals realign, forming new textures and patterns. Marble, for example, begins as limestone. Under pressure, it becomes denser and more crystalline, yet it retains traces of its former existence, a quiet reminder that change need not erase identity. Geological time is divided into eons, eras, periods, and epochs. These divisions help scientists understand the unfolding of Earth's history, from the earliest formation of the crust to the rise of life. Unlike human calendars, geological time is expansive and serene. The passing of 1,000,000 years is a brief interval in the Earth's chronology. Perhaps the most soothing concept in geology is uniformitarianism, the principle that the processes shaping the Earth today, such as erosion and sedimentation, operated similarly in the past. Rivers carved valleys then as they do now. Waves shaped coastlines then as they do now. The continuity of these processes suggests stability beneath apparent change. In studying geology, one learns that the ground beneath us is not static, but alive with slow transformation. Yet its pace is patient. It reminds us that enduring change unfolds quietly, often unnoticed, across the vast landscape of time. The dance of tectonic plates. Beneath the continents and oceans lies a dynamic system of vast, slowly moving segments known as tectonic plates. These plates form the outer shell of the Earth, the lithosphere, which is fractured into multiple sections that fit together like an immense mosaic. Though they move at only a few centimeters per year, their motion shapes the entire surface of the planet. The theory of plate tectonics, developed in the 20th century, unified many earlier geological observations. It explained why continents appear to fit together, why earthquakes cluster along certain lines, and why mountain ranges rise in long arcs. Rather than a static crust, Earth's surface is revealed as gently mobile, floating atop a more pliable layer called the asthenosphere. There are several major tectonic plates, including the Pacific, African, Eurasian, North American, South American, Antarctic, and Indo-Australian plates. Their boundaries define the most active geological regions of the world. Yet their motion is gradual and continuous, more like the slow drift of ice on a quiet sea than a sudden collision. Plate boundaries occur in three principal forms: divergent, convergent, and transform. At divergent boundaries, plates move apart. Magma rises from below, cools, and forms new crust. The Mid-Atlantic Ridge is one of the most prominent examples, a vast underwater mountain chain where the ocean floor slowly widens. This quiet creation of new crust is constant, steady, and patient. At convergent boundaries, plates move toward one another. When an oceanic plate meets a continental plate, the denser oceanic crust descends beneath the lighter continental crust in a process known as subduction. This descent generates volcanic arcs and deep ocean trenches. The Andes Mountains along the western edge of South America are a result of such interactions. When two continental plates converge, neither easily sinks. Instead, they compress and uplift, forming towering ranges such as the Himalayas. Transform boundaries, by contrast, involve plates sliding horizontally past each other. The motion is lateral and restrained, yet it can release energy suddenly in the form of earthquakes. Even so, these events are expressions of long-term motion, tension gradually building over decades or centuries before being released. The movement of tectonic plates is driven by heat from the Earth's interior. Convection currents within the mantle slowly circulate material, transferring thermal energy outward. Though invisible to human eyes, these currents provide the gentle force that propels the plates above. It is a reminder that deep, unseen processes sustain surface transformations. Over millions of years, plate motion rearranges the continents. Supercontinents form and fragment in cycles spanning hundreds of millions of years. The ancient supercontinent Pangaea, for example, assembled roughly 335 million years ago, before gradually breaking apart. Today's continents are fragments of that once unified landmass, drifting slowly across the globe. This ceaseless motion does not convey chaos, but continuity. Mountains rise, erode, and rise again. Oceans open and close. Landscapes transform, yet the underlying processes remain consistent. In contemplating plate tectonics, one recognizes that the Earth is neither rigid nor hurried. Its movements are deliberate, almost meditative, a slow choreography unfolding across geological time. The dance of tectonic plates teaches that even immense forces can act gently when measured against eternity. Beneath our feet, the planet is always in motion, yet its rhythm is vast, steady, and profoundly calm. The quiet power of volcanoes and magma. Volcanoes are among the most visible expressions of the Earth's internal energy. Yet, despite their reputation for violence, most volcanic processes unfold gradually, governed by steady thermal circulation deep within the planet. The heat that drives volcanism originates from residual energy left over from Earth's formation and from the slow decay of radioactive elements within the mantle. This heat moves outward in an unhurried cycle that has persisted for billions of years. Magma forms when solid rock partially melts under high temperature and pressure. This melting often occurs at tectonic boundaries, where descending plates introduce water into the mantle, lowering the melting point of surrounding material. The resulting magma is buoyant and begins to rise through fractures in the crust. Its ascent may take thousands of years, moving slowly through networks of chambers and conduits beneath the surface. Not all magma reaches open air. Much of it cools underground, crystallizing into intrusive igneous rocks such as granite. These bodies may remain hidden for millions of years before erosion exposes them. In this way, even unseen volcanic processes contribute to the architecture of continents. When magma does reach the surface, it emerges as lava. Lava flows can be gentle and deliberate, spreading outward in glowing rivers that gradually darken as they cool. Basaltic lava, low in silica, is especially fluid. It creates wide shield volcanoes with broad slopes that rise gradually from surrounding plains. These structures are built layer by layer, eruption by eruption, in a rhythm that emphasizes accumulation over spectacle. More viscous lava, rich in silica, moves slowly and tends to trap volcanic gases. Over time, pressure builds beneath the surface. When released, it may produce ash clouds or pyroclastic flows. Yet even these dramatic events are part of a longer continuum of geological balance. The energy released during eruption reflects decades or centuries of internal adjustment. Volcanoes also shape the chemistry of the atmosphere and oceans. Gases such as water vapor, carbon dioxide, and sulfur compounds are released during eruptions. In Earth's early history, volcanic outgassing contributed significantly to the formation of the atmosphere. Thus, volcanoes are not merely destructive forces, they are agents of planetary evolution. The landscapes formed by volcanic activity often become unexpectedly serene. After lava cools, it hardens into textured surfaces marked by ripples and folds. Over time, wind and rain soften these forms. Soil develops from weathered rock, and vegetation gradually takes root. Regions once defined by heat and fire transform into fertile valleys and quiet forests. Certain volcanic formations display remarkable geometric beauty. Basalt columns, created as lava cools and contracts, form hexagonal patterns that resemble carefully arranged architecture. Obsidian, a volcanic glass, reflects light with a smooth, mirror-like surface. Pumice, filled with tiny gas bubbles, is so light it can float on water. Each texture records a distinct cooling history. Most volcanoes spend long intervals in dormancy. Beneath their slopes, magma chambers may slowly crystallize and solidify. The mountain appears tranquil, integrated into its environment. Only careful monitoring reveals subtle signals, small earthquakes, temperature changes, or gas emissions, indicating that internal processes continue. In contemplating volcanoes, one perceives a balance between intensity and stillness. The visible eruption is brief. The underlying processes are enduring. Heat rises, rock melts, pressure builds, and the crust adjusts, all within a framework of geological patience. Volcanism demonstrates that transformation is not inherently chaotic. It is part of Earth's continuous self-regulation, redistributing heat and creating new terrain. Beneath every quiet volcanic slope lies a history of fire, and within every eruption lies a reminder of the planet's slow and persistent vitality. The slow sculpting of mountains and erosion. Mountains are often perceived as symbols of permanence. Their peaks rise above clouds, their ridges stretch across horizons, and their mass suggests immovability. Yet, geology reveals that mountains are temporary features in Earth's history, formed by uplift and gradually reshaped by erosion. Their grandeur is not static, but part of a continuous cycle of construction and transformation. Mountain building, or orogeny, typically occurs when tectonic plates converge. As continental plates collide, layers of rock compress, fold, and thrust upward. This process may span tens of millions of years. The Himalayas, for example, continue to rise as the Indian plate presses against the Eurasian plate. Even so, the rate of uplift is slow, measurable in millimeters per year, a quiet ascent unfolding across deep time. Once mountains rise, erosion begins its patient work. Wind, water, ice, and gravity act steadily upon exposed rock. Rainwater seeps into fractures, freezing and expanding in colder climates, gradually breaking rock apart. Rivers carve valleys through persistent flow. Glaciers, though slow-moving, grind stone beneath their immense weight, sculpting U-shaped valleys and smooth ridges. Erosion is not a force of destruction alone. It is also a force of redistribution. Sediments carried away from mountains settle in distant plains, deltas, and ocean basins. In this way, the material of one landscape becomes the foundation of another. A grain of sand on a beach may once have been part of a distant peak. Over vast spans of time, mountains are reduced to rolling hills, and hills to plains. Yet tectonic uplift may begin again, raising new ranges from ancient rock. The Appalachian Mountains of eastern North America, once comparable in height to the Himalayas, are now worn and gentle. Their rounded summits reflect hundreds of millions of years of erosion. Water is among the most consistent sculptors of terrain. Rivers follow gradients, gradually deepening their channels. Meanders form in floodplains, and canyons emerge where rivers cut through uplifted plateaus. The Grand Canyon illustrates how persistent flow over millions of years can reveal layers of geological history, each stratum exposed by gradual incision. Wind also shapes the land, particularly in arid regions. Fine particles carried by air abrade rock surfaces, smoothing edges and creating sculptural forms. Sand dunes migrate slowly across deserts, forming ripples that echo the motion of waves in water. Though deserts appear still, their surfaces are in quiet motion. Glaciers represent another powerful yet measured force. These massive bodies of ice move centimeters to meters per day, slowly reshaping landscapes beneath them. As glaciers retreat, they leave behind polished rock surfaces, moraines, and clear alpine lakes. The valleys they carve reflect both strength and patience. Gravity contributes through processes such as landslides and rockfalls. While individual events may occur suddenly, they result from prolonged weathering and structural weakening. Even these moments of movement are part of the larger rhythm of erosion. Mountains teach that endurance does not mean resistance to change. Instead, they embody balance between uplift and erosion. The peaks that inspire awe today are part of a cycle that has repeated throughout Earth's history. Their sculpting is continuous and measured, guided by natural forces acting with remarkable consistency. In geology, no landscape is final. Every ridge, valley, and plain reflects an ongoing dialogue between internal forces that build and external forces that wear away. The slow sculpting of mountains reminds us that transformation can be steady and harmonious, an unfolding process shaped by time itself. Rivers, oceans, and the gentle movement of water. Water is among the most persistent and patient forces shaping the Earth. Unlike tectonic uplift or volcanic heat, its motion is visible and familiar, yet its influence is vast. Rivers, oceans, rainfall, and currents form a continuous system that circulates across continents and basins, gradually redistributing energy and material across the planet's surface. Rivers begin as small streams, often originating from mountain springs or melting snow. Gravity guides them downward, gathering strength as tributaries join. Over time, flowing water deepens channels, smooths stones, and transports sediments. A river's current may appear gentle, but its cumulative effect across thousands or millions of years can carve valleys of immense scale. As rivers descend from mountains into flatter terrain, their character changes. Steep, narrow channels give way to broader valleys, Meanders form in lowland regions where water flows more slowly. These sinuous curves reflect balance between erosion on outer banks and sediment deposition on inner banks. The river shapes its path through repetition rather than force. Floodplains develop as rivers overflow during seasonal high water. Though floods can seem disruptive, they enrich soil with fine sediments carried from upstream. Agricultural civilizations have long flourished along riverbanks because of this steady renewal. In this way, erosion upstream becomes fertility downstream. Where rivers meet the sea, they form deltas, intricate networks of channels and wetlands created by accumulated sediments. The branching patterns resemble veins or roots, reflecting organic geometry shaped by flow. Deltas are dynamic yet balanced systems, gradually extending land outward into coastal waters. The oceans represent the largest reservoir of water on Earth, covering more than 70% of the planet's surface. Beneath their calm horizons lies a complex pattern of currents driven by wind, temperature, and salinity differences. Surface currents move warm water across vast distances, moderating climate in many regions. Deep currents circulate slowly through the ocean's depths, completing cycles that may take centuries. Waves, though repetitive and rhythmic, are expressions of energy transfer rather than mass movement. Water molecules oscillate in place as energy passes through them. Along coastlines, this steady motion smooths rock surfaces and shapes beaches grain by grain. The sound of waves breaking reflects this continuity, motion without haste. Tides add another dimension to water's rhythm. Caused primarily by the gravitational interaction between Earth and the Moon, tides raise and lower sea levels in predictable cycles. Coastal ecosystems adapt to this regular rise and fall, thriving within boundaries defined by lunar motion. Water also participates in the broader hydrologic cycle. Evaporation lifts moisture into the atmosphere. Condensation forms clouds. Precipitation returns water to land and sea. This cycle operates continuously, linking mountains, rivers, and oceans in a global exchange. Each droplet may travel through multiple states, vapor, liquid, ice, across centuries. In geological time, water's influence is profound, yet measured. Canyons deepen gradually. Coastlines shift slowly. Coral reefs grow millimeter by millimeter. Even vast ocean basins expand or contract in response to tectonic motion beneath them. The gentle movement of water demonstrates that persistence outweighs intensity. Through steady flow, rhythmic tides, and quiet circulation, water shapes landscapes and climates alike. It connects distant regions and sustains ecosystems, acting as both sculptor and sustainer. In contemplating rivers and oceans, one observes a balance between motion and tranquility. Water is rarely still, yet its movement follows enduring patterns. Across continents and centuries, it flows according to gravity and heat, maintaining a calm continuity that defines the surface of our planet. The language of rocks and fossils. Rocks are more than solid matter beneath our feet. They are records. Each layer, mineral grain, and fossil fragment carries information about conditions that existed long before human observation. Geology often describes rocks as pages in a chronicle of deep time. Their textures and compositions form a language, one that can be read with careful study. Sedimentary rocks are especially rich in historical detail. Formed through accumulation of particles transported by water, wind, or ice, they preserve traces of ancient environments. Fine-grained shale may indicate calm water in a deep lake or ocean basin. Cross-bedded sandstone suggests shifting desert dunes shaped by wind. Ripple marks frozen in stone reveal the direction of long-vanished currents. Within some sedimentary layers lie fossils, preserved remains or impressions of ancient life. Shells, leaves, bones, and even footprints can survive when rapidly buried by sediment. Over time, minerals replace organic material, transforming it into stone. This process, known as permineralization, allows delicate structures to endure across millions of years. Fossils provide insight into past ecosystems. Marine shells found high in mountain ranges reveal that those rocks were once beneath ancient seas. Fossilized coral indicates warm, shallow waters. Fern imprints suggest humid climates. By studying fossil assemblages, scientists reconstruct entire landscapes that no longer exist. Certain fossils, known as index fossils, help determine the relative age of rock layers. These organisms were widespread, but existed for relatively short geological intervals. When identified within a rock, they serve as chronological markers, linking distant outcrops to the same period in Earth's history. Igneous and metamorphic rocks also contain information, though in different forms. Mineral crystals record cooling histories and pressure conditions. The alignment of minerals within metamorphic rock may reveal the direction of ancient tectonic stress. Even microscopic structures can disclose temperatures and chemical environments present at the time of formation. The study of stratigraphy, the analysis of layered rocks, allows geologists to interpret sequences of events. Lower layers are generally older than those above them, a principle known as superposition. Interruptions in layering may indicate erosion, volcanic intrusion, or tectonic disturbance. Each discontinuity tells a story of change. Fossils also document the evolution of life. From simple marine organisms to complex vertebrates, preserved remains chart gradual biological transitions across eras. Extinction events, marked by abrupt disappearances in fossil records, reveal periods of environmental stress or global change. Yet even these episodes are integrated within broader patterns of adaptation and renewal. Trace fossils offer another perspective. These include footprints, burrows, and feeding marks left behind by organisms. Though the bodies themselves may not be preserved, their behavior remains recorded in stone. Such traces provide quiet glimpses into daily life millions of years ago. Reading rocks and fossils requires patience and observation. A cliff face may appear uniform at a distance, yet close inspection reveals variations in grain size, color, and structure. Subtle shifts indicate changes in environment, perhaps a rising sea level or a retreating shoreline. Through this language of stone, the Earth communicates across immense spans of time. Rocks do not speak in sound, but in pattern and structure. Fossils do not move, yet they testify to once living worlds. In contemplating these silent records, one encounters a profound continuity. Landscapes change, species evolve, climates fluctuate, but the evidence remains preserved within layers beneath our feet. The language of rocks and fossils is steady and enduring, inviting careful reading and thoughtful reflection.